So for our last talk of this section, Zachary Sisco will tell us about fungible memories. So as a normal person, I'd like to think my memories as non-fungible because you only live once. However, it turns out that this is not the case in computer hardware. So this talk will introduce the abstraction of fungible memory that pushes the state of the art on hardware compilation and retargeting for memories. Okay.
All right. Hear me? Great. Thank you for the introduction. Okay. Yeah, so like the introduction said, in this work, we're focusing on a particular hardware design problem. And so, yeah, we're proposing this language abstraction called fungible memories, which gives us a write once, map anywhere memory abstraction that hardware developers can use to target many different memory technologies from a single generic interface. Okay. In this work, we incorporate fungible memories into a memory compiler, which automatically targets many memories according to different technology constraints. And then we also go in the other direction. We also build a memory decompiler, which lifts memories from existing gate level or simulation-ready designs up to fungible memories to enable technology retargeting. Okay? And so to accomplish this at scale, we developed a structure-aware equality saturation technique which scales to net lists with millions of cells and identifies memories that state-of-the-art tools cannot. And so while we're in the equality saturation session, this work really touches on a very specific hardware design problem. And so I want to kind of set the stage a little bit, give an example, right? So how do hardware developers design memories, right? Let's consider a register file, right? So here we have a nice little block diagram of a register file, has 3 source inputs, a destination register to write to. If we're using a hardware description language like Verilog, we would normally describe it like this in a behavioral way, right? We can model our register file as a two-dimensional register, or a two-dimensional array of registers. We can use familiar array notation to read to it, to write to it, and that's great, right? This works fine for simulation. If we want to deploy this to something like an FPGA or any real piece of hardware, this kind of implementation does not always work, okay? And the reason is that languages like Verilog do not provide technology-specific constructs in the language, right? A device like an FPGA has things like BRAMs to describe memories. And Verilog doesn't really know what a BRAM is, right? Now, there are some mitigations to this, which I'll talk about in the evaluation, which we compare to. So in this case, what does a developer do if they want to deploy this on an FPGA or an ASIC or anything like that? Well, they need to write a custom mapping for this register file to be able to map it to BRAMs on a particular FPGA, right? So in a language like Verilog, what we see a lot are these if-def blocks. So developers will split parts of their code for each memory into a separate if-def for each technology target that they want to work for, right? And so our developer here will make a new if-def block for their FPGA target. And so what did they put in here? Well, for that particular FPGA, they'll read up into their, they'll pull up their vendor manual that describes how to instantiate that BRAM, and they'll figure out how to do it. This is one example of a particular mapping. It has all these different parameters and ports that they have to hook up in the right way, right? And it's not always that easy because this mapping can be a little tricky, right? It's not always the case that we have a one-to-one mapping between our behavioral memory design and the one that would conform to a particular technology, right? And so in this example, the interface for our register file has 3 read ports and 1 write port. A typical FPGA may only support dual port BRAMs. And so the developer actually has to make a custom mapping which will kind of map their 3 read port, 1 write port memory into a configuration of multiple dual port BRAMs, which emulates the behavior of a 3 read, 1 write memory, okay? And so these are transformations that the developer has to make, okay? And this is just the register file. This is a little data path diagram of a CPU. If we're developing a CPU, we have many more memories in our designs. This mapping process has to be repeated for each of these different types of memories, and they have their own configurations and semantics as well, right? So this makes refactoring a pain on the code base, right? If we want to support new technologies, we need more if-def blocks if we're using this kind of technique. If we change the behavior during the development process, the design process, we need to refactor those blocks in a consistent way, right? And so the takeaway here is that technology constraints make this implementation brittle to design changes, right? And the language that we're using, Verilog, isn't really providing us any helpful abstractions. And so that's where fungible memories come in. So a fungible memory enhances our hardware description language because we try to capture the shape and connections and portedness of memory blocks in hardware designs. Okay? So in this paper, we formalize an algebra of fungible memories where ports and memory blocks are objects that can be constructed and rewritten according to a set of semantics preserving rewrites. Okay? This is a list of just kind of the different rules that we include in the paper. This involves splitting memories by read ports, write ports. We can also merge them together. We also do rewrites according to the shapes of our memories. You could split by width and height and so on. We can also do casting between port configurations as well. So this is an example of a read port splitting and merging rewrite. Right? We could start with a memory that has k read ports, and we could split one of those read ports out into a whole separate memory block in this way. So the visualization is on the top, and how we actually formalize it as a memory is on the bottom. Okay. We can also support other kinds of kind of function splitting and merging as well. Certain memories might support optimizations like write-to-read forwarding, where you would forward the value of a write to a read port, right? Some memory blocks would support this as a flag, and some don't. And so depending on your technology constraints, you would either want to kind of fold that logic into the memory if it's supported, or if it's not, you want to break it out into separate logic so that you could still map the design, right? And so in the paper, we describe a handful of other rewrites over a fungible memory algebra, and then they have various, we have a formalization of that. And the last thing I'll mention about this is because this fungible memory algebra is kind of introducing a sort of new equational theory of memory blocks and hardware, we wanted to have some confidence in it. And so we formalized fungible memories in Lean because we wanted to prove that the rewrite rules that we constructed actually preserve behavioral equivalence according to memory read-write semantics. So that's described a little more in detail in the paper. The Lean source code is also in our artifact as well. Okay, so with fungible memories in hand, we incorporate that into an existing hardware description language so that we can do this automated memory technology mapping, right? The problem kind of roughly looks like this for our memory compiler, where we have a set of fungible memories, we have some technology constraints, and we want to try to figure out, using our rewrites, how can we reshape our memories to fit the technology constraints? And that gives us a satisfying mapping, right? So as one concrete implementation of this, we extended Pertle, which is a Python-embedded hardware description language, to support fungible memories. As one particular case study, we ported a 5-stage RISC-V CPU to use fungible memories. One benefit of this is that we were able to kind of shrink our memory implementation in Pertle from 130 lines of code to 3, one for each memory block in the design. So a very kind of declarative memory specification now. And this also comes with the benefit of getting a bunch of different technology backends for free. So that's something that Pertle really just focuses on simulation, but now with this automated technology mapper, we can then target many different memory backends. Okay, so that's the memory compiler direction. The other direction for this is the memory decompiler, right? And so this is important for this memory retargeting scenario, right? And so there's a lot of different kind of more and more open hardware designs out there. It's common more and more for developers to compose their designs kind of with different components, put them together. And some of those may have been developed with a different technology in mind, or maybe developed with maybe just technology abstract, right? So what if we wanted to integrate those components into a new design and retarget it to a new technology? That's where memory decompilation comes in. We want to identify these memories in our design and lift it up to fungible memories, okay? So the way that we do that, I'll kind of give a really brief overview of how this works. So this would, in kind of the most basic case, you would start with a gate level netlist, and you would analyze that gate level netlist You have all the different flip-flops and logic and try to identify memory blocks in there, right? So the first step would be grouping flip-flops into wider registers based on common enable signals, and then kind of building out different memory block candidates. We have a set of rewrite rules for identifying read port logic, which often works over like a mux tree reduction. We have kind of a symmetric set of rewrites for identifying write port logic, which kind of works over demux reduction. And then putting all those things together, we then identify all those common pieces and extract all the different fungible memories in that design. And so the key technique to doing this is equality saturation. And it's really kind of a perfect setup for equality saturation because we have this huge kind of blasted out gate level netlist, thousands, even millions of low level logic cells. And with a lot of the aggressive logic optimizations that hardware synthesis tools may perform, it's really not obvious what sequence of rewrites will reveal this kind of higher level structure that we're looking for, right? Now, for anyone who's used equality saturation, like rewriting over an E-graph with millions of nodes is not going to be a fun time. And so in order to actually implement this and get it to work, we had 3 key optimizations to help with this. The first one we call structure-aware scoped rewriting, right? And so a lot of these logical rewrites that we might perform over a gate-level netlist can apply almost anywhere in the netlist, right? And that's going to increase rewriting time and grow the E-graph unnecessarily. But since our goal is memory decompilation, we really only care about signals whose source or sink is a register. And so we do this sort of like structure-aware rewriting to really cut down on where we're applying some of these rewrites, particularly mux tree reduction. We really only care if that's connecting to register sources. So that's a really key one. Another very useful one is subsumption. During register grouping in the initial phase, we only really need to choose a single representation of grouped registers rather than maintaining every possible grouping of flip-flops. So we will subsume all other groupings. That's also a big saver. And then another really helpful one are inverse transformations. And so this comes from the Selinsky work. And this is about inserting speculative equalities into the E-graphs and later validating them. And so we adapted this to netlists because using inverse transformations is really useful when we're rewriting over netlists because hardware synthesis tools might apply these really aggressive optimizations, which we need to undo to kind of reveal some latent structure that was hidden by those optimizations. So that's a very helpful technique there as well. Got it. And then the last one, and this is probably the most twisted one, is that we implemented our equality saturation engine in SQLite, okay? And and so we know from egglog and other recent research that there's this beautiful connection to relational databases and equality saturation. And we took this to the extreme, and to good effect, I would argue, right? And so kind of doing things directly in SQL, we could really easily implement a lot of these optimizations without maybe some of the guardrails that equality saturation frameworks might impose. And certain phases, like grouping registers by common signals, we can do those kinds of queries very fast in relational databases, right? And so this kind of helped us break some rules for doing decompilation, which I would argue, since we're decompiling anyways, it's okay to be a little messy. And so we could sometimes skip some expensive steps, which normally come up, okay? And so putting all of this together, we have this tool called Memo, which comprises the compiler and decompiler for fungible memories. It looks like this. The user would either input a design expressed in Perl extended with fungible memories, which will then go through the automated memory technology mapper alongside different technology constraints. We have a number of backends spanning simulation platforms and ASIC and FPGA memory technologies. And then alternatively, a user can input an existing design as a netlist, go through the memory decompilation step, use those fungible memories to then retarget to a new technology. I'll briefly go over a bit of our evaluation here. We have more details in the paper, But a big aspect of evaluating this is actually with the memory decompiler, because this is enabling us to compare over existing designs and compare with related techniques, right? And so in this table, we have a handful of open source hardware components that include things like caches, FIFOs, a couple of small RISC-V cores, and other SoC components, right? And so in each of these designs, there is an expected memory. And sure enough, we were able to decompile and identify those memories in their kind of original configurations. Decompilation time is fast for these. And what we wanted to do is we wanted to compare it with something that was the most similar kind of operation to what we're doing. And that would be memory inference in hardware synthesis tools. And so hardware synthesis tools like YOSYS and other FPGA synthesis tools have a thing called memory inference, which is more of a syntactic pattern matching operation, where it looks at the Verilog code, kind of matches over a syntactic template. And if you don't perfectly match that, then it's not going to identify the memory. And so memory decompilation works over the structure of the net list rather than just a syntactic template. And so we're able to identify memories over designs that YOSYS missed and even some commercial tools missed. We have a handful of large-scale case studies from some open source hardware designs where we do memory decompilation and then also do retargeting to different FPGA and ASIC technologies. One example is the Spark core has the netlist that we decompiled had more than 700,000 gates. Memory decompilation took about a minute, and we recovered all of the expected memory blocks. A bigger one, we decompiled an L2 cache. That was 1.5 million gates. Took about 2 minutes, and indeed we correctly identified all the expected parts of the cache: tag, state, data blocks, and all of that. And then our biggest case study was the open source Black Parrot RISC-V multi-core SoC. The kind of synthesized code for this is about 12 million gates. Memory decompilation took about 6 minutes, and we went through and checked, and we identified all of the expected memory blocks in that core, in the front end and the back end. Okay. And so to wrap things up, kind of more broader level takeaway, I think in hardware description language design, technology specialization is perhaps a bit overlooked. I think there are indeed some useful abstractions that we can kind of pull out to improve the development process in this way. I think fungible memories are one instance of this observation, right? So we developed this kind of equational theory of how we can think about memory design, and then using powerful rewriting techniques like equality saturation, we can improve different aspects of synthesis like tech mapping. And we can do it at the scale of real-world SoC designs. And so my question is, what other equational theories are hiding in the hardware development process that we can kind of think about and build into our tools? So, like I said, our tool memo is open source. That is the compiler and the memory decompiler and its lean formalization. I would encourage you to check it out. And yeah, thank you all very much.
Well, thank that. We have time for 2 questions.
Sometimes the synthesizer may using some correlation analysis to identify that some parts of the memory is dead and it could be eliminated. In that case, the signature of the memory is changed. Is that a problem in your tool, or we are stay faithful to the user's specifications?
Sure, yeah, this actually comes up really importantly in our write port decompilation stage. So when we're looking at things like register files in CPU designs, a lot of times we would find that the synthesis tool would kind of erase the demux, like the parts of the demux tree related to the 0 register, right? Things like this. And so that's where techniques like inverse transformations really help us, because they help us undo some of those aggressive optimizations that synthesis might do. Yeah, so that is one example of that.
Okay.
Thanks for the talk. It's a bit sad to see that people would rather use SQLite than Egglog. But I'm curious about your experience, like building an eGraph engine on top of SQLite. Like, what's good and what's bad about that?
Let me first say I love Egglog. I think it is a wonderful tool, and we did a lot of prototyping with it. I think the experience of writing an equality saturation engine in SQL, I think is arguably worse than writing one in Egglog, because it's like you're writing SQL queries and things like that. So it's not as ergonomic as a language that was designed for doing what it was like what Egglog does. But I think that the trade-off is we had so much more direct control over the schema, like over what we were doing. We were able to kind of be a little more messy. I would be interested in seeing, is there a front end to this to kind of describe what we were trying to do and then compile that to SQL instead of having to, I mean, you can check out our open source tools and see what the SQL looks like, and it's kind of gnarly, but it makes sense when you look at it a little closer, but it's not that fun. Not as fun as Egglog.
Okay, let's thank Zach again.
Thank you.
So just as an extra plug, Zach is also looking for prospective students and postdocs. So if you are interested in quality saturation, computer architecture, or program language in general, please talk to Zach. And this concludes our equality saturation session.